Good evening. Uh, we're back sharing some of the accomplishments that I have been making here at Plain Space Design. Uh, so we're going to talk about the most recent thing that I have done. And it's no surprise that I'm back into trying to find the equation for the perimeter of an ellipse. I mentioned that there are a lot of avenues that were never tried that one could take in order to find a closed form equation for the perimeter of the ellipse. And so one of my ideas that I was going to try this time was to parameterize the equation for the ellipse differently than it had been done before. Usually it would be parameterized in terms of the angle theta, and that is the parameterization that leads us into the trap of getting an unsolvable integral, the elliptical integral, for which there is no closed form solutions. Therefore, if we try to parameterize it differently, then that might have us achieve something that is solvable. So my idea was to try to find some function f of AB that I could use to integrate and therefore find a closed form. So I sort of went straight to what the ending of the process would be. We would find an integral f of AB, and if it was a circle, then if we were to integrate it for one quadrant, then we would come up with 1/4 2 pi r for one quadrant, and say, well, I could start there and work backwards. That was my plan. But what happened was that I began to realize that I would end up with a integral equation where the thing that I was solving for, the function, would be under the integrand, and those are once again another type of rabbit hole that we could end up going down. Therefore, I said, well, let's not start doing those type of solutions, and instead we should focus on a path that I mentioned earlier, and that is to use geometry to try to find an equation and not end up in algebraic traps. And this is where I began to see some success on this day. So I abandoned this integration attempt, and I started finding formula based upon the surface area of a cylinder. And the unique thing about this cylinder is it has a circular base, and the height of the cylinder equals the perimeter of the base. So this is a specialized cylinder with this specific condition imposed upon it. And for a circle, since we already know the perimeter of a circle, that turned out to be a good model for us to start with. So here I I have here, I was going to calculate the surface area of the cylinder. And if the height was equal to the perimeter of the base, then that would be, in this equation, h equals 2 pi r. So the formula for the surface of a cylinder with a circular base, the surface would be 2 pi r squared twice, the top and the bottom, plus 2 pi r h. That would be the area of the lateral portion if the cylinder was unwrapped into a square. Then the sides would be of length 2 pi h. That's one side of the square. 2 pi r, excuse me. That would be the perimeter being unwrapped into a straight line. A straight line would have the length 2 pi r. And then the h would be the vertical side of that figure, of that area. Adding all of these together, we get the area, surface area of a cylinder with a circular bottom. Now, since I chose to make the cylinder have the perimeter and the height of equal magnitude, I could substitute for h in that formula another 2 pi r, and so the second term would become 4 pi squared r squared. And then I noticed that at this point I had the area of the base occurring in both terms. So I was going to factor that out. In fact, it's twice the area of the base. The top and the bottom occurred in both terms. So I factor out 2 pi r squared, and that would leave me with 1 plus 2 pi. So a circular cylinder with the height of the cylinder equal to the perimeter of the base could be described by this formula: 2 pi r squared times 1 plus 2 pi h. That would be the surface area of that object. So since we know the formula for the area of the base of an ellipse, I switched to an elliptical base just by just plugging it in to the circular cylinder formula and turned it into a elliptical cylinder by simply using pi AB, the area of the top and the bottom, as the area of an ellipse, a formula that we know. Now, that is sort of it's just a shot in the dark, really, because there's no guarantee that an immediate substitution like that would give the desired result. So I tried it and paid no attention to the derivatives at the top, or the square base attempt over there. None of that. Well, this was just a test to see if this formula was work for any base shape. And it was pretty close for a square base. The square base would have a perimeter, if it was 4 units, would have a perimeter of 16. And when I plugged it, the same things, same area substitution in here with d squared being the area of a square of size 4, it came up with 14. I considered that a failure though. But here's how I use the formula. I tested it on a ellipse with semi-major axis equal 3, semi-minor axis equal 2 units. And I calculated it out. And then when you solve for h in this formula, in the surface area formula, you're essentially solving for the perimeter of that ellipse, because they were set to be equal when in the circular model, and then when we substitute the area of the ellipse instead of the area of the circle, then we modified the circular equation, sort of transformed it from a circular to an elliptical equation. So we solve for h, which would be the square root of the surface minus 2 pi ab. Of course, I have the 2 at the end here, so it's pi ab2. And when I calculated what the perimeter of that ellipse would be, I got a value 15.39059. And when I used an online perimeter calculator to test it against that value, I believe it came up 15.4 or something. It was a very close value. I said, well, I've got something here then. It's going to do that every time. So I tried it again. This time on an ellipse with a 9 semi-major axis and a 6 semi-minor axis. And I went through the same procedure, calculated h, which would also be equal to the perimeter p, according to the way we set the model up. And it turns out that the value I got after doing that was also close. I came up with 46.17179 in this result, and in the calculator that I was using online, I believe I got 47 point some number. So once again, it was really close. Then I thought, well, maybe I can develop that, find another way to find h that didn't even involve the perimeter of an ellipse, but has all known factors. And I said, well, let's take a look at the volume of an elliptical cylinder. The volume is pi abh, and we can solve for h as the volume of pi, the volume divided by pi ab. And then with the surface of the elliptical cylinder, it has a perimeter equal to the height it would be, the surface would be 2 pi AB plus A squared. However, I kind of lost my grasp on what the next step would be at that moment. Maybe I just wanted to lock in on what I had previously achieved and was not ready to go on to any improvements just yet. So I was going to try to transform the ablative circle formula into an iterative formula by replacing HP in the surface formula with the result from the previous calculation in an iteration process squared, to see if that would just work like the Newton approximation process, where you just gradually iterate until you get the correct answer. I had that idea, but I didn't work it through thoroughly, and when I wrote a program to try it, it just kept giving me the same number for H again. So I need to work on that, but it seems like a Newton-Raphson iteration formula would, as used in astrodynamics, for instance, to find certain factors in equations, orbital dynamics. It works there, and I'm suspecting that it will work here as well. So locking in on the previous work, I decided to go and write some Python code to begin to test the things that I had accomplished there. So here is the Python code that will calculate this Python code will calculate the surface area of an elliptical cylinder. So we bring in the math, calculate the area of the two elliptical bases. That is known, pi AB. Multiplied by 2, so we got the top and the bottom of the cylinder. And then to calculate the area of the lateral portion, the side, we need to find the perimeter of an ellipse. And this equation uses Ramanujan's first approximation, which everyone has a lot of high regard for, to calculate the perimeter. And so the lateral area, the side around the side of the cylinder, would be that perimeter of the ellipse times the height of the cylinder. And then this program calculates the total surface area. And we run it for an ellipse with semi-major axis 5, semi-major minor axis 3, and we print out the total surface area. So now I modified that to give me the perimeter ellipse. So I calculate the area of the two elliptical bases as previously done, pi AB, multiplied by 2 to get the top and the bottom, then the surface, the lateral base. I approximate the surface area with my formula that I had found. The surface is equal to total base area, that's 2 pi AB, times 1 plus 2 pi in parentheses. And then to solve for the height of that particular cylindrical, elliptical cylinder, excuse me, elliptical cylinder, I would use the formula h equals the square root of the surface minus 2 pi ab, total base area. As before with my hand calculation, then it would return that height, and that would represent the perimeter. So I tried it on an ellipse with major axis of 9, semi-major axis of 9, semi-minor axis of 6. Calculate that perimeter using the function that I just described and printed it out. And then I would use Ramanujan's first approximation to get a value to compare it with to see how good my geometric formula did. And this is what I came up with. The geometric perimeter was 46.1718. Algebraic perimeter was 47.5963. That's Ramanujan's value. And the difference was about 2.9929%. Which is pretty close. And let's run it again using the value here. The value was 5 that was originally in there, and this value was 3. And if we were to run it with these values, let's see what we get. And we get the value for my geometric parameter was 24.3347. Ramanujan's algebraic parameter 25.5270, and that's 4.6788%. So that's like really close. Every time I come in under Ramanujan's values. And here's a second run, a third run, where I try to use to add a right here, an iterative approach to see if I could accomplish something similar to Newton just on the first try, Newton's approximation procedure. And I ended up getting the same value both times when the semi-major axis was 9 and the semi-minor axis was 6, as it was before I changed it in the previous cell. Got the same percentage, the same numbers. But the point here is that I always come in under Ramanujan's, this formula. I'm not saying me, because I'm not in there doing this, but this formula, this geometric approach, comes in slightly under Ramanujan's approach, but it is a far less number of parameters to deal with. So geometry seems to be giving some nice, neat formulas to work with as compared to the algebraic complexity that the formulas that have been developed previously have been doing. And I don't know which one is closer to the actual value, but most people would say it's Ramanujan's because it's a time-tested equation. But it might be the better of the two formulas still. But the fact that I'm closing in on that path with far less work, far less manipulations for a number of terms, simpler formulas. That's promising. So that's what I'm doing this very day at this time here at Plane Space Design. So, if I can get this to come back to me. That was today's accomplishment, and I am glad to share my work with you. Thank you for listening to my ramblings about geometric elliptic formulas. I hope that it inspires you to try to do something similar with your time. Good night.